This is the first discussion for Chapter 12, solids, the physics of solids. We're going to look at crystal structure, density, and elasticity. Something that you may not be aware of is that for metals and things with ionic bonds, the atoms are lined up in crystals. More than what we get into now, they actually have a few different patterns of crystals that they align in. And we know this from the early 1900s from X-ray diffraction, that you could actually see X-rays bounce off the atoms and make a shadow pattern. There are materials like glass and putty that do not arrange into crystals, and those are called amorphous. But more materials are crystalline than you might think. For future reference, the atoms in a solid can be bonded ionically, covalently, metallically, or what we call a van der Waals force, which is the weakest. The eventual property of the solid material is a function of, among other things, the kinds of bonds that are, the way the atoms are held together dictates the property of the material in the form that you and I would deal with. There's also, it's the size of the nucleus of the atom and how closely that they're packed together also tells us about the density of the material. Density is a good thing, a good property of material that you'll need to remember. People sometimes confuse it with the size of something or the massiveness of something, but it's actually how much mass is in a given volume. And we'll either talk about it in kilograms per meter squared or grams per centimeter squared. This will come up a lot again in liquids when we talk about buoyancy and why do boats float, why do airplanes fly. Will have to do with the density of an object. We can also look at a weight density, particularly if you're in imperial units, which is rather than the mass, substitute instead of that the weight divided by the volume. So that could be pounds per cubic foot or newtons per cubic meter. When we look at weight density, like anything else dealing with weight, is it weight on the Earth or someplace else? So don't forget our acceleration due to gravity of about 10 meters per second squared. If you're looking at a weight density, if you're going from the mass of something to its weight density, you'll have to take into account the pull of gravity on the material. So like I mentioned before, density has to do with the massiveness of the individual atom and how closely the atoms are packed to each other. And it's a property of the material. Other properties of material are things like whether or not it's magnetic, whether or not it reflects, whether or not it conducts electricity. And properties of material doesn't, so long as you're not talking about a minuscule amount of it on the atomic level, the property of material doesn't matter on how much material you have, and density is the same way. Another property of material is its elasticity. Think about a piece of elastic or a rubber band. When we talk about the elasticity of a material, it's how much it will stretch and then go back to its original form. So this is not talking about something that we would deform. If we take a piece of putty and smash it flat, then that would be a material that is inelastic. If they don't go back to their original form, they are inelastic. But when we're talking about a material being elastic, it's something that we can change the shape of, and the material goes back to its original form when we remove our force. Question, what do you think is more elastic, steel or rubber? I'm not talking about a rubber band, I'm talking about rubber. And the answer to that actually is steel, because it can bend, it can bow, it will go back to its original shape, whereas rubber is more like a putty sort of material. When we talk about the elasticity of a material, we use a proportionality that we call Hooke's law. Hooke predates Newton. Hooke is more along the time of the Great Fire in London. Christopher Wren, Boyle, he's actually doing work before Newton's work. I believe he died before Newton was born. Newton was incredibly jealous of him, uh, which is kind of a funny thing. But Hooke, among other things, looks at the elasticity of springs. Now, springs are fun to play with, but we're actually looking at them here as a alternate to a solid piece of material. We could do this with a solid piece of material, but we would have to take some very, very fine measurements. If we do it with a spring, it's pretty easy. And basically, when we're looking at a spring, we're just saying that the, the distance that we change is exactly proportional to the amount of mass or the force on which we're pulling the spring. So Hooke's law is telling us that if the force doubles, the displacement doubles. If the force goes up by 4, the displacement goes up by 4. If the force goes up by 1,000, the displacement goes up by 1,000. Until this is only when the material is still in its elastic range. If we extend a force to the point that the material deforms permanently and doesn't go back to its original state, then it's no longer in its elastic range. We've taken it to the point of inelasticity. Hooke's law is pretty simple, pretty straightforward, nothing unusual happening here. So, if I have a spring and a 1 kilogram mass makes it stretch 12 centimeters, when I triple the mass, how much is the load? How much is the displacement going to be? Um, the point on this one is to look at the way the question is worded, and it's saying that a 10 centimeter spring extended to 12. So it only stretched 2 centimeters. So when the load would triple, that 2 centimeter stretch would triple into 6 centimeters. So instead of being a 10 centimeter long spring, it would be a 16 centimeter long spring.